This is your presenter Asloob Mudassar, and I am presenting slide number 114 of the course on laser physics. Question is, derive the optimum output coupling conditions for a 4-level laser system in the space-independent and space-dependent models. The answer is, consider a 4-level laser system in the space-independent model with output power given by P out is equal to AB times AS times gamma 2 by 2 times PPE over P threshold minus 1, where IB is the cross-sectional area of the pump beam, IS is the saturation intensity, gamma 2 is the output coupling, that is the coupling through the mirror 2, PPE is the electrical power to the pump, P threshold is the threshold power out from the pump, and minus 1. So this equation, that is P out, has been discussed in many of the previous slides. You can see any of the previous slides, for example, slide number 110 and onward to see the details about this P out. Let us assume that T2 is the transmission of the output mirror 2 under a fixed pump rate, which is PPE, that is PPE is fixed, which maximizes the output power called optimum output power, and we denote it by P out, P opt, comma out, which is the optimum power out. When laser operates at P optimum power, the transmission through the mirror 2 may be referred to as the optimum transition. Optimum transmission denoted by capital T2 opt, opt for optimum. If T2 is made greater than T2 opt, the output power tends to increase. That is, P out becomes greater than the optimum power out from the pump. This results in the decrease of number of photons in the cavity, which brings the output power back to P opt. So if our transmission of the mirror 2 becomes greater than the T2 opt, then of course the output power will increase, and this will decrease the number of photons in the cavity, which will bring the output power back to its optimum conditions. Similarly, if T2 is made smaller than T2 opt, the output power tends to decrease. That is, the P out becomes smaller than P optimum output. This results in an increase in the number of photons in the cavity, which brings the output power back to P opt. That is, back to the optimum output power. For optimum transmission, we impose the condition that the rate of change of output power with the coupling losses from the mirror 2, which is gamma 2, that is dP out over d gamma 2 is equal to 0. For fixed PPE, that is the fixed pump power, so P out depends on P threshold, which is given by. Here you can see that in equation number 1 over P output depends upon the value of the P threshold, that is the threshold pump power, and the threshold pump power is given by equation number 2. For this one you can consult some of the previous slides. So P threshold, that is the threshold pump power, is equal to gamma over eta P times H nu MP divided by tau and times A over sigma, where gamma is the total losses per pass in the cavity, eta P is the pump efficiency, nu MP is the minimum frequency from the pump, tau is the lifetime of the upper level, and A is the cross-sectional area of the active medium rod. Sigma is actually cross-sectional, the cross-section of the spontaneous emission, where gamma is equal to gamma I plus gamma 1 plus gamma 2 divided by 2. Gamma 1 is the loss associated with mirror 1, gamma 2 is the loss associated with mirror 2, gamma I is the internal losses in the cavity. And this capital gamma on the left hand side is actually the total, is the sum of all the losses within the cavity. So that is P threshold depends on the value of gamma 2. We can express a P threshold as P threshold is equal to, so let me show you the expression for the P threshold, which is given in equation number 2. And we are now going to insert the value of gamma over here, and gamma is equal to gamma I plus gamma 1 plus gamma 2 divided by 2. And when we use this relationship, we have shown, you see that in the parenthesis, we have substituted the full value of gamma. And the terms in the red is that we have taken this term, that is gamma I plus gamma 1 divided by 2. This has been taken common from this whole parenthesis. And in the parenthesis, we are left with 1 plus gamma 2 divided by 2. And then, of course, this whole term in the denominator. And then, of course, the rest of the quantities are the same. So now we can rearrange the term and combine some terms in the curly brackets shown in blue, which is gamma I plus gamma 1 divided by 2. Then this term is multiplied by 1 over eta p, then multiplied by h nu mp divided by tau, then multiplied by a over sigma. So this term in curly bracket will be labeled as the minimum threshold pump power. And then outside that one we have, because the remainder of the term is what in over here is 1 plus gamma 2 divided by 2, and then divided by gamma I plus gamma 1 divided by 2. So this is the term at the end outside the curly bracket, which is shown over here. So you see that we can label the minimum threshold pump power, which is the power shown in the curly bracket, and denote it with PM threshold. And then, of course, we can write 1 plus, the last parenthesis can be written as 1 plus capital X, where capital X is the term shown in red over here. This is capital X. Where PM threshold, that is the minimum threshold power, is equal to the P threshold power evaluated at gamma 2 is equal to 0. So if you put gamma 2 is equal to 0 in this expression, if you set this gamma 2 is equal to 0, you will get this P threshold to become equal to P minimum threshold. So this is what shown over here. That is P minimum threshold is equal to P threshold. That is the threshold power evaluated at gamma 2 is equal to 0. And if you put gamma 2 is equal to 0 in the previous expression that I have shown you, then we are left with this gamma I plus gamma 1 divided by 2 over eta p, and then the rest of the quantities, which are h nu mp divided by tau, and then a over sigma. So you see that this is the term. This is actually the minimum threshold power, which we have also shown in the curly bracket over here. And you know that this capital X is what I have shown explicitly now, that capital X is equal to gamma 2 divided by 2, and then this term is divided by gamma I plus gamma 1 divided by 2. Where PM threshold, that is the minimum threshold pump power, is equal to the threshold pump power evaluated at gamma 2 is equal to 0, where PM threshold is the minimum threshold pump power or the threshold pump power for zero threshold coupling. And zero threshold coupling means that gamma 2 is equal to 0. That is, no light is going out of the cavity. That is, the mirror M2 is not allowing the light to go out or to escape from the cavity, which means that gamma 2 is equal to 0. That is, the coupling losses due to the mirror M2 is 0. So substituting M threshold from equation number 4 into equation number 1. So this is equation number 4. That's P threshold is equal to P minimum threshold times 1 plus X. And we are going to substitute this one in equation number 1. This is equation number 1. So we are going to replace P threshold in equation number 1 by its value shown in equation number 4. That is this value. That is P threshold is equal to P minimum threshold value times 1 plus X. So substituting this one, we have the following relationship over here. So P threshold is equal to gamma I plus gamma 1 divided by 2 plus gamma 2 divided by 2. This is the full expression for the P threshold. Okay, actually this is what I have already explained. Now this is actually the output power. So you see that this is the output power from equation number 1. And you see that I have replaced the P threshold, that is the threshold power has been replaced by the term from on the right hand side of equation 4, which is the PM threshold multiplied by 1 plus capital X. So this is whole equation 1, and P threshold has been replaced by PM threshold, that is the minimum threshold value times 1 plus X from equation number 4. And we have introduced XM parameter over here, where XM is equal to a ratio of PPE, that is the electrical power to the pump, divided by the minimum threshold power from the pump. So this ratio has been designated as XM in this equation. So you see that if you label PPE divided by M threshold by a parameter XM, then of course then this term becomes XM divided by 1 plus capital X. Okay, now what we are going to do is that we are multiplying with gamma I plus gamma 1 divided by 2, and we are also dividing gamma 2 divided by 2 by this term. So multiplication and division by this term shown in red. So this again you will see that gamma 2 divided by 2 and divided by gamma I plus gamma 1 divided by 2. This is nothing but capital X. So this term will be replaced by capital X, because capital X is what we have explained over here, that this is capital X. So now we have this term P out is equal to AP times IS times gamma I plus gamma 1 divided by 2, then multiplied by X, then multiplied by XM divided by 1 plus capital X minus 1. So this is equation number 5. So you see that over capital X is proportional to gamma 2, which you can see from this expression, that capital X is proportional to gamma 2. So which also implies that the derivative of P out with respect to gamma 2, which we want to set equal to 0 in order to optimize the output power with respect to gamma 2. For that one, we have to take the derivative of dP out over d gamma 2, and we have to set this derivative is equal to 0, so that we can find P out of an optimum value of P out. And you know that this is equivalent to dP out over dx, that is the derivative of P out with respect to capital X should be set equal to 0, because both are equivalent. Because X is a proportional to gamma 2, so the derivative with respect to gamma 2 means that the derivative with respect to capital S will also produce the same results. So in equation number 5, you are going to take the derivative of dP out with respect to dx, for example, as shown over here, and then you will set that derivative equal to 0. And the derivative will be equal to this one, because the derivative will operate on the x terms only, which I have shown over here. That is d over dx operating on the curly bracket, which contains capital X times xm over capital 1 plus capital X minus 1. And we have set this derivative equal to 0. So if you take the derivative of this derivative, you will get and solve for the value of x. This value of x will be labeled as x opt, which is the optimum value of x. And if you solve this equation, you will find capital X is equal to square root of xm minus 1. And this capital X will be referred to as the capital X OPT, that is optimum value of capital X. So you have to substitute capital X by this value. That is, you need to put the X optimum in the equation over here. For example, at the value at the place of X, X is present over here and X is also present over here. So you can replace this X by the value of square root of xm minus 1, and then simplify this equation, which will give you that now the P output power will be labeled as P optimum output. That is, the optimum output power will become equal to AB times IS times gamma I plus gamma 1 divided by 2, and then we have this term extra, you see, which is obtained when equation number 6 was used in equation number 5. We obtained this term, which is the square root of xm minus 1. And you know that this expression will give you the optimum value of the output power, of course, from the mirror 2. When xm is fixed, x opt, that is the optimum value of x, is also fixed, and so the output power, that is the optimum output power, will also be fixed. It can be deduced from these equations that when the output coupling capital X changes around the optimum coupling value x opt by a large percentage, say by 50%, then P out is lowered by a small percentage, say 5% of the optimum output power. That is, the optimum output power is relatively insensitive to the changes in the output coupling around x opt. So if you change capital X by a value in the vicinity of the optimum X value, then of course the changes to the output power, which is the optimum output power, will be very small. It has been found that the equation number 6 can still hold for space dependent models. That is equation number 6 that we have derived for the space independent model for a 4-level laser system is also applicable to space dependent models for 4-level laser system. P out for uniform pumping. So you see that there are two cases that we can report the value of P out: for uniform pumping or for the Gaussian pumping. And P out for uniform pumping and Gaussian pumping are respectively obtained from the following XY relationships. So for the uniform pumping, I have used red color for that one, and this is given by over here. For the uniform pumping, this is the XY relationship, and for the Gaussian pumping, this is the XY relationship. And these relationships are valid for the space dependent case, for the uniform pumping shown in red and for the Gaussian pumping shown in green. We can use these relationships where x and y are given by x is equal to PPE over PM threshold and y is equal to P out over PS, where PS is the saturation power, P out is the output power, and PPE is the electrical power to the pump, and PM threshold is the minimum threshold power out from the pump. And the corresponding equations for the P minimum threshold, that is for the minimum threshold power, are respectively given by. So this is the minimum threshold value for the uniform pumping case for a 4-level system, which is a space dependent system. The minimum threshold power is given by this equation shown in red. And if you are using a Gaussian pumping for a space dependent case of a 4-level laser system, then the minimum threshold power is shown in green, where WP is the beam spot size of the pump beam, sigma E is the stimulated emission cross section, eta P is the pump efficiency, gamma I is the internal losses, gamma 1 by 2 is the loss, is the coupling loss due to mirror 1, and here MP is the minimum pump frequency required to carry out the species from the to carry out the population from the ground state to the upper level. Tau is the lifetime of the upper level. So you see that I have explained here the output conditions shown over here in the form of P output, that is the output power, output pump power from the laser for a 4-level laser system for the space independent case. So this expression is shown, you see, in equation number 7. And this expression is also valid for the case of space dependent cases. And for the space dependent cases, because you see that in the derivation of these equations, we have used the value of P threshold value over here. That is the minimum value, minimum threshold power has been used in the derivation of this expression. And I have also given these two expressions over here. Red one is the for the case of uniform pumping for the space dependent case for a 4-level laser system, and the P minimum threshold shown in green is for a Gaussian pumping for the space dependent case for a 4-level laser system. So this completes my answer. So this is the end of slide number 114.